Greenhouse gas effects describe the specific mechanism through which certain atmospheric gases trap heat near Earth's surface. While carbon dioxide receives the most attention, other greenhouse gases include methane, nitrous oxide, and fluorinated gases, each with distinct chemical properties and heat-trapping abilities. Methane, primarily from agriculture and waste management, traps approximately 28 to 36 times more heat per molecule than CO2 over a 100-year period. Nitrous oxide, released through agricultural practices and fossil fuel combustion, has nearly 300 times the warming potential of CO2 and remains in the atmosphere for over a century. The greenhouse effect itself is actually essential for life on Earth, maintaining temperatures approximately 33 degrees C warmer than they would be otherwise. Without any greenhouse gases, Earth would be a frozen planet. However, the enhanced greenhouse effect from human activities disrupts this natural balance. For instance, warming from these gases triggers feedback loops like permafrost thaw, which releases stored methane and further accelerates warming beyond direct human emissions. These chemical processes happen at molecular levels but manifest in planetary scale changes. Addressing greenhouse gas effects involves technical solutions across sectors. Carbon capture technologies aim to pull CO2 directly from industrial emissions or the open air, potentially storing it underground or converting it to usable products. Agricultural innovations focus on reducing methane from rice paddies and livestock through modified farming practices and feed additives. Refrigeration and air conditioning industries are transitioning away from hydrofluorocarbons to alternative coolants with lower warming potential. These targeted approaches complement broader climate action strategies by addressing the specific chemistry of different greenhouse gases rather than treating all emissions as equivalent. Information technology systems have become significant contributors to greenhouse gas emissions worldwide. Data centers consume vast amounts of electricity, much of it still derived from fossil fuels, with estimates suggesting they generate as much carbon as the entire airline industry. The manufacturing of electronic devices requires energy-intensive processes and rare earth minerals, whose extraction causes additional environmental damage. Planned obsolescence in consumer electronics creates mountains of e-waste containing potent greenhouse gases used in cooling systems. The rapid growth of cryptocurrency mining has further intensified energy consumption, with some networks consuming as much electricity as medium-sized countries. These technological systems accelerate carbon emissions while often being marketed as environmentally neutral or beneficial. Remote sensing and Earth observation technologies offer promising approaches to greenhouse gas management. Advanced spectral imaging satellites can now detect methane plumes from specific industrial facilities and pinpoint leaks in natural gas infrastructure with precision previously impossible. These systems enable regulatory agencies to verify emissions reporting and identify violations in near real time. By combining satellite data with ground-based sensor networks, scientists create comprehensive emissions maps that reveal previously hidden pollution sources. This integration of aerospace technology with environmental monitoring demonstrates how targeted innovation can strengthen climate accountability even as other technologies contribute to the problem.